All right, now I'm going to introduce reaction quotients, and probably one of the most common questions I get from students whenever I've helped them with 222 stuff in the SRC, or I've tutored students, or I've taught a class and I've talked to people outside of class. One of the most common questions I get is just, what is Q, and why? How is it different than the equilibrium constant? I don't understand how they're different. And that confusion comes from the fact that the expression for Q looks identical on paper. The way we calculate Q is the exact same as how we calculate the equilibrium constant. We products over reactants to the power of their stoichiometric coefficients, but we have a Q here instead of a K. What does that mean? Well, we have to back up, but that's where the confusion comes from. So KEQ is our ratio when we are at equilibrium. Now, systems reach equilibrium spontaneously. They make it happen on their own. I don't have to make it happen, but they aren't necessarily always at equilibrium. It takes time to reach it. If we start with something that's out of equilibrium, it has to equilibrate. It has to take time and reach that equilibrium. And so what Q is if I just look at it right now, maybe it's at equilibrium, maybe it's not, but if I just look at it right now, I don't know it's at equilibrium, I'm just checking it. I can calculate Q. Now, if I plug in my values for my concentrations, I put them in the expression, and I get a number that's identical to KEQ, my system is at equilibrium. So Q and KEQ can be the same numerically, but fundamentally they're different properties, because Q is where are we right now, KEQ is my ratio at equilibrium. So this is like your bank account. You get paid and then you pay bills. And so at equilibrium, there's some amount of money you have. You get your paycheck, it goes up. You're probably not at equilibrium because you got to pay rent, you got to pay electricity, you got to pay internet, you got to pay the phone, you got to pay whatever, you got to go buy groceries. You start approaching, you're going back to equilibrium. But for that moment, that paycheck comes in, Q's looking really good, right? But then it declines. Eventually you hit equilibrium by the end of the month, which when I was a student was about 0, I'll be honest. So I've been there. That's your equilibrium position. And then boom, you get paid, and then it declines, so on and so forth. Really it was more like into the quarter because I had financial aid money, but whatever. Because it's not like I was working a job that paid all my bills while being a student. For those of you that do that, tip of the hat to you. I only work part-time. I don't know how anyone does more. Where was I? Besides, either making you love or hate me. I don't know which, one of the two. Someone's really mad that I didn't work full-time while going to school, and someone's really happy that I congratulated them on it. Whatever. Okay, so that's the difference between Q and K. So Q is just like here and now, here and now. What is it? What is it? Maybe we're at equilibrium, maybe we aren't. Q is what we check to see if we're at equilibrium, if we know what it's supposed to be. Now, there's QC, there's QP if we use partial pressures, so be aware of that. Just like there's 2 versions of K, there's 2 versions of Q. I'm only going to do concentrations because, I don't know, I guess I have a strong bias that way. So if we look at an example here. So we have H2 plus I2 gives us 2HI. Might look familiar. I don't like to shuffle my examples too much. Well, if all of our concentrations are equal and 0.1 molar for all of our reactants and products, what's Q going to be? Well, we write our expression for Q. Then we plug in our number. So we have HI squared, because there's 2 of them, over H2 times I. Ooh. That got a little exciting. I mixed up some stuff there. All right. Good thing I do such heavy editing, so you'll never see this happen. Okay, there we go. If anyone's ever seen the movie Ed Wood, he's a strong influence for my approach to this class, apparently. The Kool-Aid Man could go running through the wall. I wouldn't edit it out. I'd just roll with it. All right, so 0.1, 0.1, 0.1. We just plug them in. We get 1. Now, if K is supposed to be 1.2 times 10 to the 8, which we actually calculated earlier in the previous video, are they at equilibrium? Is 1 the same as 1.2 times 10 to the 8? No. No. This system just got cut a hell of a paycheck. It is way over equilibrium. Like billion over equilibrium or something, or a couple hundred million, whatever it is. I'm too lazy to look at my decimal places right now. I've been talking too long today. And, side note, I don't know if you've seen, I'm trying not to limp around in these videos today, but getting old sucks. I think I might have broke my toe getting in the shower last night. How do you do that? And of all the times, they can't do anything about a broken toe anyway, but it'd be nice to know I could go to a hospital catching a I don't know, a potentially fatal respiratory illness or something. All right, I've made my toe feel better. And they say complaining doesn't solve any problems. All right, and that's true, by the way. It is a giant purple pinky toe right now, which you don't know how often you use your pinky toe till it's maybe broken. Anyway, 1 and this are not the same, so we are not at equilibrium. If they were, we would be, okay? So then we can ask the question, well, how is it going to shift? Is it going to make more products? Is it going to make more reactants to reach equilibrium? And to do that, we just go, well, if K is less than Q, so if Q is larger, it's going to make more reactants. It's got to back up. And if Q is smaller than KEQ, it's got to make more products. It's got to proceed forward. And so we don't have enough HI, right? In fact, we know from before, if this is 0.1, this is 0.1, this needs to be 0.7, if you remember our old example. And so we're going to have to shift overall right. We're going to have to produce more. Now, it's not that the reverse reaction isn't happening, it's just that the forward reaction is going to occur faster, and eventually they'll equilibrate at equilibrium. So that's what's going on. So this system has to shift more to reach equilibrium. We are not at it yet. So just because something has an equilibrium doesn't mean you are always at equilibrium. For example, our biological systems like our cells are horrifically out of equilibrium. You reach equilibrium when you're dead. All of our life we are fighting equilibrium. Our cell is fighting equilibrium constantly. And then when we finally give in, take that last breath, our system returns to equilibrium, and then we smell bad, so we get buried or burned or whatever. And then that speeds up the equilibrium process of turning us back into CO2 and whatever else. Always an exciting class. We've talked about a pandemic, my broken toe, and now death. So cool. This is usually what every day is like. Man, it's amazing I held off this long. But anyway, just got to get it in there. We're on the last chapter. I was getting real anxious. Really wanted to make sure you guys were thoroughly depressed before you took this chapter test. Because, you know, you'll be so sad to be done with my class. But yeah, so that's the difference. So again, if you look at this expression, you go, well, what the hell is different between K and Q? That's the exact same thing. And the answer is, it's the exact same formula. It's used in different circumstances, okay? And this is what we can do with it. We can use it to compare and see if we are at equilibrium. And hopefully that'll help you avoid that main kind of trip hazard with this material. All right, so we're going to talk about systems that have multiple phases of matter and how we address that in our equilibrium constant. And yeah, and then we'll be on to some very fundamental stuff with Le Chatelier's principle, and then the really fun mathematical stuff at the end of the chapter using Rice tables and so on and so forth.